So, hello everyone. My name is Josie-Harrison. I'm an interdisciplinary PhD student in the computer science and architecture departments at Chalmers University. And my research focuses on using machine learning to detect reusable building materials for circular construction. And today I'll be presenting this paper titled Scalability in Building Component Data Annotation that was written together with Yinan and Alexander Hollberg. So construction and demolition waste is a growing concern for many countries. Unfortunately, most construction and demolition waste is still being disposed of in landfills despite efforts by government organizations to divert it. One of the primary barriers to integrating waste material into new buildings is lack of visibility into the available materials that could be recovered. The barrier could be reduced if detailed inventories were known several years ahead of demolition. But this leads us to the question, what is the most effective way to create these reusable building material inventories? So several researchers are investigating computer vision methods to potentially create these material inventories using street-level photography, such as Google Street View, because of the ability to essentially turbocharge material identification. So this comes along with machine learning has several benefits that it can offer. Automated material identification can process large data sets quickly and consistently, leading to increased scalability. Machine learning algorithms can analyze pixel-level details to accurately identify materials and images, often surpassing human capabilities, which leads to a reduction of errors. And also, machine learning algorithms are more consistent at following a defined taxonomy. And just creating this taxonomy itself reduces a lot of the ambiguity in identifying materials. So the process to detect materials from Google Street View could look something like this, where we first capture the Street View image. We identify which parts of the image belong to a building. And then from those masks, we classify the facade material for each building, although there's several alternative ways to do this process. The problem for many people working on this topic that they confront at some point is that the first step is often quite difficult. For machine learning, more data is always better, but it can take quite a long time to manually annotate images. Also, collecting a random sample of coordinates for training data doesn't necessarily guarantee a class distribution that accurately reflects a specific area. So for example, someone is interested in collecting training data that contains the labels brick and stucco from a certain area, and they selected 1,000 GPS coordinates for Street View images. But there's no guarantee that this will be half brick and half stucco, or that even brick and stucco will exist in the dataset at all. Luckily, in the last couple years, the capabilities of image generation may now be at a level where it's possible to train a model on synthetically generated images. There are many ways to generate images, but for this study, we decided on text-to-image generation using OpenAI's DALL-E because of its ease of use and the potential to make highly diverse images. Studying the potential of synthetically generated images as training data is worthwhile because of a few benefits. There's a potential to reduce the time needed to annotate images. A fully realized solution would just require the name of the material of interest, and from that point, you could make an unlimited amount of images within minutes. Synthetically generated images could augment data sets where not enough images of a specific material were collected from GPS coordinates. And synthetically generated images have the potential to create data sets where materials that are typically difficult to photograph, like office interiors. So these two images show examples of, the first one's a bit weird, but these two images are examples of images I made with DALL-E. I was interested in getting examples of stone, and I would say they're quite realistic. There were 3 main experiments conducted in the study that were built off of the Urban Resource Cadastre dataset, which is a public dataset created by Deepika Raghu et al. From ETH Zurich, which is available on GitHub. So we started with keywords for prompts. We turned these keywords into text prompts using language enhancements. And from there, we generated the images. We trained the Swin Transformer model from those images. And then we evaluated on either entirely manually annotated data or synthetic data. The augmented experiment corrected the class imbalance that was seen in the URC dataset. The mixed experiment trained entirely on synthetic data, but was evaluated on manually annotated URC dataset. And the synthetic experiment was trained and evaluated on entirely synthetic data using labels that didn't exist in the URC dataset. The sub-experiments isolated the experiment to 3 classes, which were other, null, and the label of interest. And doing this, isolating it to the sub-experiments allowed us to reduce the parameter space, which allowed for a higher resolution model. There was a baseline experiment that essentially replicated the results from previous studies and was used as a comparison. For the synthetic images, we had a language enhancement that was used to increase the diversity in the text prompts. This process used a simple text generation model to generate sentences from keywords, and this sometimes had the effect of the images straying too far away from the reference. So we used a brute force image quality filter, although this could be probably automated in the future. These 3 experiments were curated in a way to evaluate the error distribution to see how closely they resembled the error distribution to the baseline. As such, there are a few characteristics of the datasets that are worthwhile to mention, since the different datasets had different sizes for the experiments and the classes. For all the experiments except the synthetic, the labels siding, stucco, other, and null were used. For the purely synthetic experiment, stone, glazing, and concrete were studied. Some of the sub-experiment data sets were quite small because they were limited by the size of the URC dataset, specifically the augmented dataset and the mixed siding sub-experiment, which had an effect on the performance, as you'll see on the next slide. So the overall results is that while manual annotation remains the gold standard, the synthetic data demonstrates a promising alternative. The first graph is an ROC curve, which shows the black line that goes through the diagonal. It represents a random classifier. So if we had a model just predicting at random, that black line would represent the effect of that. And all the experiments are well above that black line, which shows that they are performing better than random. On the right are the confusion matrices from the baseline, augmented, and mixed experiments. From the augmented confusion matrix, we can see that the augmented stucco sub-experiment had a higher performance than the augmented siding sub-experiment because these two had different ratios of synthetic to manually annotated data. The augmented stucco sub-experiment brought better performance than the baseline, though. So it becomes clear that there's a ratio where the benefits of augmenting the data set can decrease as we increase the synthetic data. And the stucco mixed sub-experiment at the bottom left had a much better performance than the siding mixed sub-experiment at the bottom right, because the training data set was much larger, which leads us to believe that training with synthetic images requires a larger data set than training with manually annotated images, because the texture details become lost in this process. So I mentioned earlier that language enhancement was used to encourage diversity in the generated images. This generated sentences from keywords that we gave into the models. There were some surprising results that came from this that I thought would be interesting to share. First was these nonsense prompts that are very not grammatically correct, but had surprisingly good images come from it. So the first sentence says, "The building made of old stone in BC has a bulbous period." The second, "The building constructed of the entablature called the Renaissance." And the third says, "The building made of brick built in New York City has a current size of 3.6%. So these prompts are very silly, but they made some nice images, so I was happy with that. The second is that sometimes the model really wanted to force words onto the image. So here, the model was really obsessed with the word stucco and was trying to do variations of it onto the image, but it wasn't very successful at actually typing out the word stucco. So we had to filter these out of the training data set. The third, sometimes the model was very artistic and made these very contemporary artistic buildings. These also needed to be filtered out. And finally, sometimes the model made very strange images that have no relation to Google Street View, and these also had to be filtered out. So in summary, synthetic data as a solution has a lot of potential, and there are a few key aspects to getting good performance if you want to do something similar. So the language enhancement to increase the diversity in the training data was a very essential component. Maximizing the resolution of the model, there's a limit to whatever hardware you're using. If you use too high of a resolution, then you'll get an out-of-memory issue. So it's very limited by whatever hardware is being used. And third, reducing the problem space to the minimum number of labels that you need helps alleviate this memory issue and allows for a higher resolution model. So the next steps for this study will be to synthetically generate images for office interiors, but it could be also any other images that are normally difficult to get access to. So thank you. Again, my name's Josie, and thank you for listening.
Thank you very much. Thank you. Any questions?